Okay, so welcome to the next topic of chemical principles 2, and in this particular part we are going to talk about statistical formulations of the second law. So, we have seen from the classical descriptions of the second law and classical descriptions or evaluations of entropy, rather formulations of the entropy formula from Carnot cycle and all. There we have learned that entropy increase is favorable. However, we did not understand from that why entropy increase will be favorable. So, we have learned that reversible heat change at a given temperature is entropy, and therefore, essentially entropy is some similarity, there is a similarity of entropy with heat energy, because it is a reversible heat. Then the common notions that entropy is associated with chaos or disorder or randomness is somehow does not come from that particular description, unless we say that heat energy is nothing but random motions of molecules. We know that heat is proportional to temperature, and that is how we actually derived in the earlier part the heat expression or formulations of heat came from the earlier part. And we have seen that temperature in principle is nothing but the kinetic energy of the particle, and by kinetic energy we know that it is proportional to velocity square. So, in a way we are talking about, when you are talking about heat, we are talking about random motions of molecules having certain particular velocities, and we can vaguely associate that with the entropy. So, which means that if the motions are more vigorous, more random, velocities are somehow higher, we can associate roughly to an increase in entropy. But it does not give us a certain feeling that why that will be something that will keep on increasing with time. How do we get the time arrow? How do we know that certain events like falling of an egg and breaking it when it hits the floor is an entropically increasing process? We have discussed that when something falls, it hits the ground, and that energy which was initially potential energy converted to kinetic energy, and that energy get dissipated among the molecules of the floor, and therefore, we do not get it ever back. That means, for the reverse process to happen, all the energy that got dissipated in the atoms of the floor has to do a exactly same reverse motion in order to push that egg back, and that is unlikely, an unlikely event according to our own understanding and feeling. However, to get more concrete idea, we have to talk about second law, that in the context of the fact that the entropy of the universe is increasing is true only on average. That means, the second law is true only on average. So, it is, and when you talk about an average, we talk about a statistical outcome of certain occurrences. The fact that this cannot happen, the reverse process, that all the particles of the floor cannot come back and push the broken pieces of egg and all other things together and pushes it back to our hand, is because that the second law is a statistical law. So, the fact that entropy of the universe is increasing is true only on an average. It is a statistical outcome of certain occurrences. However, where is the statistics in the breaking of an egg? If the egg falls and breaks, we do not get to see the reverse process, and where do we understand, from where we do understand that there is some statistical outcome associated with that. So, in order to do that, we have to delve deep into the constituents of a macroscopic system. By that what I mean is that we have to see that every macroscopic system like cricket ball or an egg or a glass of water is made of tiniest, smallest particles like atoms and molecules. So, while it is required that only smallest number of variables like n, v and t describe the equilibrium properties of a macroscopic system. By that again I will remind you that if you want a bottle of water from a shop, you say that I want a 1 liter bottle at room temperature or thanda. So, if you say thanda, which means 4 degrees centigrade, if you want room temperature, then it is whatever 27 degrees centigrade, and you specify the volume, and you do not have to specify the pressure, but that is already specified. So, by saying these three variables, you are specifying entirely a macroscopic system. However, actually what it requires is specifications of 10 to the power 23 variables, not only 10 to the power 23. So, there are, as you know, that in 1 mole, so 1 liter of water has 55.5 mole, which means it has 55.5 multiplied by 6.023 multiplied by 10 to the power 23 number of molecules, multiplied by 3 will be the number of atoms, and every atom has 3 positions and 3 momentum coordinates. So, multiplied by 6 will be the number of variables that are required in order to specify the state of a particular system. Only one difference though, for macroscopic systems we can only specify the equilibrium properties with n, v and t, smallest number of variables. However, for microscopic systems we can specify any state of the system by specifying all the variables, especially classically. We are talking about classical system. Here we are not going into quantum systems, where actually on top of these coordinates you also have to specify the other things like electrons. We don't have to consider about electrons, at least in classical descriptions. We only consider atoms and molecules. So, coming back, so once we know the position and the momentum of all the particles, we can then obtain any property we like, and that is the subject that is known as statistical thermodynamics or molecular thermodynamics. So, this subject will help you to calculate entropy as a statistical outcome of things. Remember, again we will use the configurations of these atoms and molecules to predict what will be an observable thermodynamic property. For example, if I talk about pressure or volume, we will be able to calculate from the motions of atoms and molecules. The pressure that you observe is actually an average pressure. It always fluctuates around the average. When you say 1 atmospheric pressure, it is just on an average it is 1 atmospheric. When you talk about volume, on an average it is 1 liter. If I specify 55.5 mole water's volume is only on an at room temperature, only on an average it is 1 liter. It will be always fluctuating. So, macroscopic properties, and we will show that it is nothing but the average properties obtained from statistical distributions of these atoms and molecules. However, it is not possible to precisely state this humongous number of variables and conditions. As I said, 50.5 multiplied by 6.023 into 10 to the power 23 into 3 into 6 is not possible. Therefore, probabilistic approaches are used in approaching the properties of thermodynamics using atoms and molecules description. So, these probabilistic approaches will not give us individual detail. However, it will give the property according to the average outcome of them. For example, we will give an example. So, in quantum mechanics also we have seen that given a wave function we can calculate the average expectation of the expectation of certain property, which are nothing but averages over all possibilities. So, we do not have to know there that how an electron moves, still we can get the average property right. So, although not quite similar, but in this classical descriptions also, once we know the entire distributions of systems, we will be able to calculate the average property. So, connection between thermodynamics and statistical thermodynamics is probability, which will provide us an average expected outcome, as I said. Now, let us see some examples of how probability helps us to obtain a good understanding of the outcome. For example, if we ask, will it rain tomorrow? And if we know all the conditions of like how the rain happens, and measure all the properties like humidity, air pressure, in a given range of certain kilometers, if we calculate the grid wise pressure and humidity and use some Navier-Stokes equations and solve that, probably almost deterministically, unless the condition is not turbulent and all that, we will be able to predict whether it will rain tomorrow or not. It requires huge computations, and actually meteorology department will do that. However, we can resort to a probabilistic description. Will it rain tomorrow? And we need some informations. For example, in the month of November, what is the probability of having rain? So, has it rained in last 20 years in the month of November, or has it been raining for last few days? So, these are the things that will help us to calculate the probabilities whether it will happen or not. Of course, probability always means that it is not certainty, but it means that if we do many observations, then we will get that as an average. So, with some confidence we will be able to say that whether it will rain tomorrow or not. So, another important thing about the statistics is that, as I said, it is more accurate when there are more sample points. That means more observations, it will give us better averaging. So, therefore, statistics in chemistry especially works, because when you talk about observations, we have huge number of observations in terms of Avogadro's number of molecules. So, our sample points is huge, because we are not doing the statistics on 10 particles or 20 particles, we are doing that on 10 to the power 23 number of particles. So, I will give you an example that how the large number of observations help the probability. So, many of us know that the casinos where the gambling takes place, there are like slot machines where you put some small amount of money and you can get a benefit, or let us say you put 25 cents and you may get like $2 or more in the slot machine. But the slot machines are designed in such a way that it is slightly in the favor of the casino, let us say 2%. So, 52% the probability is that the casino will win is 0.52, and probability that everybody else will win is 0.48. So, which means that if you play once or twice and you may get lucky, however, if you keep on playing, then eventually you will lose, because it is the slot machine is designed to have the probabilities in favor of the casinos. So, now if you play, you do not have to play so much, we will give some examples. If you play 1000 times, the probability already will be in favor of casinos. Now, imagine if you play 10 to the power 23 times, what will happen? It will be almost exact to the value that casinos will actually be winning. So, now coming back, why entropy increase is favorable? We do not understand that so well from classical descriptions. However, statistically we can say that entropy is nothing but options. What I mean by that is that exactly like what is written, more entropy is more options. So, for example, if I have an option to be anywhere in the campus, I will be found anywhere in the campus. If I am constrained to be in the room, I will be, so my options are limited to only the room. So, which entropy is higher, when I am all over the campus or when I am only inside a room? So, intuitively you can feel that of course, entropy when I can be anywhere in the campus will be higher, because there are more options. I can be found in the mess, in the hostel, in the field, anywhere. So, obviously more choices, more options are there when I am free anywhere in the campus. Within the campus, let us say I am bound. Similarly, this options will always play a role whenever you can think about entropy. So, what is the possibility when something falls and hits the ground, that the energy will be distributed? Let us say if there is no option to be distributed, it cannot, but if there are particles in the floor that can absorb those energy, more particles are there, there will be more options for the energy to be dissipated. So, the statement of the second law from the statistical point of view is that every system, if left to itself, will on the average change towards a condition of maximum probability. So, we have to know about the system. Left to itself means we do not put any constraint. On the average, which means since it is a statistical law, it is not deterministic. We will see that entropy will not always increase, there may be decrease also, and it will change to a condition of maximum probability, which means that wherever it will find a most probable situation, it will go there. So, we will talk about probability then, because it is going towards maximum probability. So, we will talk about that in a moment. We will give an example that what we mean by most probable situation, and yeah, we will come back to that. So, in a nutshell, different arrangements of atoms and molecules is called microstate. So, every arrangement of atoms and molecules is a microstate. Statistical thermodynamics is a theory that connects those microstates or those arrangements to something called bulk matter, meaning a glass of water, a cylinder of gas. So, a cylinder of gas or a glass of water is a macro state, where we do not care about atoms and molecules. We only care about the state defined by some number of particles. It can be anything, their configuration, their momentum, their positions do not matter. We need to know only volume and temperature. These are all called macroscopic variables, whereas these are microscopic variables, position and momentum. Microscopic variables, and in short form we write that by R n. So, there are n particles, R is a vector x y z to the power n, means there are n number of vectors, which means 3n number of positions, and p n is momentum. So, this defines a system. Our system is defined by this, whereas in the macroscopic system, a glass of water, let us say it is a 250 ml glass. So, I know the n, I know the p, and I know the temperature. Temperature is let us say room temperature. So, 250 ml means it is 1/4 of a liter, right. So, 55.5 by 4 into 6.023 into 10 to the power 23 number of into 3, because I am talking about water. So, atoms will be into 3, and then pressure is 1 atmosphere and temperature is let us say 27 degrees centigrade. So, these are the variables that I used for defining a macroscopic system, and these are the variables that I use for defining a microscopic system. And these microscopic systems, these motions, these positions and momentum, as you can understand that they are not going to be always same. See, this is going to be same. When the system is in equilibrium, then our n, v and t is not changing. Let us say okay, if the what if the water molecules is evaporating? No, we are not talking about that condition, because that is an open system. We are talking about the condition, let us say in this particular case NPT is a closed system, where energy can exchange. However, the number of molecules are not changing. So, we are talking about a closed system where number of particles remaining same, pressure remaining same, and temperature is also same. So, that is precisely this bottle of water. Now, this bottle of water I have defined by NPT, but believe it or not, there are all these 6.023 10 to 10 to the power 23 into 55.5 by 4 number of molecules continuously changing their positions and momentum, and each snapshot of that means if any of the positions or any of the momentum of any of the particle is changing, then it is creating a new state, and each of that is a microstate. That is what we call as microstate. So, microstate is string of numbers mentioning positions and momentum of each particle. In that string, if any element is changing, is creating a new microstate. So, now let us say if I could take a picture of frame of this at every instant of time, that would be a microstate, and all those microstates will give us an estimate to calculate the statistics from that, and of course, that will give us a thermodynamic property. So, I will show you. We really cannot take a femtosecond camera and see the positions and momentum of this one, but we can do that in computer. So, in computer what we do is we run molecular dynamics simulations. So, if you are not aware of that, what it does is that we consider each atom as some ball, a particle, and we calculate the force that is acting on each of the ball from some potential energy that is already defined, and then we propagate. The propagate meaning we change the positions of the particle with time, exactly what is expected of things happening in this bottle of water. So, we try to simulate the same system in computer, and since we do that in femtosecond time scale, we can actually capture the microstates in femtosecond. So, we are going to show you an example of such microstates from our own simulations in a moment. So, as you can see that I am showing you a system of some 1000 water molecules, and this blue, red and green coordinate showing x, y, z frame. This is a software called VMD that we use to show the trajectories obtained from simulations of these water molecules. One of the water molecule is represented in something called CPK model, just to show you that, but each of them can be represented. We are just showing one of them just to show you how the water molecules is moving, means just to tag, it is called tagging a particular molecule, and just to show that they are moving. Now, we are going to run the simulations and you can observe that. For example, we are running it now. As you can see, every atom is wiggling and jiggling, all of them, and the special water molecule that we are tagging, we can see that it is rotating, it is vibrating, and it is translating, all sorts of things happening. Now, if I stop it at any moment, this is one microstate you can think of, because at this stage all the particles have some fixed positions and some fixed momentum. I run it and stop it, another microstate, run it, stop it, another microstate. So, every instant of time gives me a new microstate, and we can use all those microstate represent this particular system. They are not talking about any other system, which means that this bottle of water has all those microstate representing the same bottle of water. So, once we do that, we get an idea that once we have all those microstates, we are going to then estimate our properties based on those microstates, right. But then is it possible to do that? If not, we have to use some other approaches in order to understand the desired calculations. So, That is why it says that it is not possible to know the position and the momentum of each particle, and therefore, we use probabilistic approach, similar to tomorrow's weather and all. Now, if we could actually estimate all the properties, all the microstates, and represent that number by W, then Boltzmann defined this formula of entropy, where entropy will be equal to Kb ln W, where the W is the number of microstates. So, if we could count the number of microstates, different possible microstates, by the way, it is not the same microstate, we do not overcount the thing. Let us say we enumerate all possible different arrangements of positions and momentum of that glass of water. We could say that S equal to Kb ln W, where W is those things. Now, what Boltzmann said, so this is 1872, remember that we talked about classical second law of thermodynamics that came around 1850s. Boltzmann worked parallelly, and that was the time that even electrons were not discovered, because electron got discovered in 1894. So, the concepts of atoms, like something was that that was the smallest thing and all. Quantum mechanics did not get discovered by then, because that came like much later in 1925. So, imagine the power of mind, where without almost any information he could come up with such a remarkable equation, where in which we get an idea and a definitive formula for calculating such a quantity as entropy. So, his idea is simple, that S is proportional to the number of microstate. It is just proportional to. That means more microstates, more options, more entropy. That is it. Now, let us I take one system W, one system I take which has a W. I repeat the same system, that also will have W, right. Now, if I calculate the microstate of the combined system, when I combine them together, you will see that will be nothing but W square. Okay, so we have to talk about what is microstate in a moment, we will do that. So, it is, so W is the number of possibilities that A can have. So, then when we say that for all possibilities of this system, what are the possibilities of this system, or for a given possibility of this system, what are the possibilities of that system, it will be W. So, in that case it will be W into W as W square. However, if we associate entropy of this system as SA, this also will be SA, and we know that entropy is an additive quantity. So, the combined system, the entropy will be 2 SA, right. So, in one case you have 2 SA and another case you have W square. That is only possible if I use an ln function, because ln of W square is nothing but 2 ln W. Now, if ln W is SA, so 2 SA will be 2 ln W. So, you see, because the microstates of combined systems get multiplied, you need the ln function, and Kb is nothing but a proportionality constant called Boltzmann constant. Note that this equation is a postulate, just like Newton's equations of motions, which does not have any origin. It is a postulate from which classical mechanics starts. This is the equation from which statistical mechanics start. We cannot go back from this. We cannot ask that, oh, where do we get that? We get that from phenomenology. Second law, first law of thermodynamics, they are also phenomenological equations. We have no so called fundamental proof that heat cannot go from low temperature to high temperature. spontaneously. It is an observation, and therefore we postulate that, and that is the Clausius statement, which then got connected to Kelvin's statement, which then got connected to all the other things, and then entropy derivations came, and then we said that entropy of the universe was increasing. So, there was a starting point, and the starting point was that phenomenological observation. Similarly, here also the starting point of definition of entropy is that it is proportional to number of microstates. If it is that, then rest of the things you will see they will unfold just from this equation, and we will be able to explain certain things the way we understand them. So, only logic that we try to give here is that while entropy is additive, microstates are multiplicative, and therefore the need for ln is there.